Unified dynamics.
If you look at the two foundational pillars of modern physics, they describe entirely different universes. General relativity relies on a completely smooth, continuous spacetime, but zoom in, and quantum field theory demands a reality built on jagged, volatile, and discrete energy states. When you try to overlap these two models, the architecture fails. Quantum mechanics requires a fixed, unchanging background to calculate probabilities. General relativity bends that background until it breaks, predicting black hole singularities where the math collapses and information vanishes. Neither framework provides a closed, information-preserving ledger. They cannot guarantee that the exact amount of data entering a physical interaction is fully accounted for when the interaction ends. Unified dynamics maps reality onto a capacity-limited simplicial complex. Every physical interaction is treated as a transport process on a network with a definite, countable bandwidth. The fundamental building block of this network is the K4 tetrahedron. It is the minimal, three-dimensional geometric structure capable of enclosing volume. Under this framework, the continuous physics we observe is an emergent statistical artifact. The smooth curves of spacetime are generated by trillions of these tetrahedra operating within a finite, deterministic matrix. This brings us to the core problem of the derivation. If the universe is actually a purely computational, discrete matrix, how do we get stable matter? A purely computational field has no mechanism to hold itself together. Without an external constraint, any local excitation or bundle of data will simply scatter at the speed of light. Stable packet formation requires a variable capable of bridging computational updates with physical geometry. We find this in the Einstein coupling constant, 1/9 pi squared. When injected into the system, this constant introduces a physical tension. It acts as a discrete geometric clamping force that strictly dictates how data can move across the network. Macroscopic matter exists because the underlying geometric tension forces computational noise into bound, persistent states. To see exactly how this clamping works, we have to isolate a single unit of the substrate, one K4 tetrahedron, and track how it transports data. The base architecture of spacetime is a finite operator algebra across this lattice. A generalized Dirac operator, D12, contains the geometric degrees of freedom. Information propagates along tetrahedral edges via a 5-component carrier state, tracking A, B, and E spectral waves from vertex to vertex. The absolute law governing this transport is conservation. The system operates as a strict ledger. Every unit of data must be perfectly accounted for during local transport. We can test this ledger by running the system under a purely topological condition, using the uncoupled OCPF Hamiltonian to see how the network updates mathematically without any gravitational parameters. The result is a failure recorded as the sigma-2 anomaly. Because a pure topological field lacks curvature, the local reference frames lack the internal tension needed to align their vectors. The information fails to latch and simply scatters off the edges. The simulation proves that a purely computational universe is intrinsically unstable. It lacks the internal structural tension required to bind moving data into persistent, recognizable states. Resolving this blockage requires us to introduce a physical constraint into the pure topology. By projecting the Einstein coupling constant into the Hamiltonian, we alter the total energy equation. The system is no longer calculating just topology, it is calculating topology plus gravity. This explicitly injects simplicial curvature directly into the computational field. The wave boundary coupling equations dictate how this new pressure interacts with the local ledger. When applied, the mathematical straight edges of the simplices begin to exhibit geometric strain, bending under the stress. Macroscopically, this local strain generates a topological potential well, a structural dip in the network. As data packets approach this well, they encounter a manifold repulsion term. It acts as a detour tax, physically impeding the free, light-speed transport of the computational nodes. The Einstein coupling provides the exact geometric tension necessary to slow these transient nodes down, forcing them to accumulate and form clustered structures. This chart tracks nodes reacting to the well. We start at n equals 1. Growing from 1 to 6 nodes, the structure remains transient, creating violent, unstable fluctuations. But hitting n equals 7, it crosses the persistence threshold and flatlines into stability. This structural shift occurs within a very specific parameter, a narrow coupling window right at 88.4. Within this window, the statistics of the network undergo a massive correction. The probability of packet closure leaps instantaneously from just 34. These locked mass packets exert intense stress on the rigid tetrahedral network, which must absorb this energy to maintain stability. The system manages the stress by distributing it across 4 specific accommodation channels. The internal closure angles shift, the spacing between packets compresses, the slack in the transport channels tightens, and the secondary branches absorb any residual overflow. Every microscopic adjustment is a discrete algorithmic reaction calculated precisely by the underlying lattice geometry. As we look at the network from a distance, a statistical coarse graining process occurs. The jagged, discrete points of structural stress blur together. The smooth, continuous spacetime curvature we observe in standard physics is a macroscopic illusion. It's the statistical stress response of a fundamentally discrete network adjusting to its own data load. This perspective redefines the terms of the canonical Einstein field equation. Gravity emerges as a direct measure of informational network congestion. Heavy N7 matter clusters physically clog the local transport lattice around them. Because of this clogging, nearby data packets cannot take a direct path. They are forced to take longer, more complex detours to communicate across the geometry. That mathematical detour tax, the physical delay of data paths around a heavy cluster, is exactly what we experience as gravitational attraction. Fundamental parameters like the fine structure constant or the Poisson ratio emerge as statistical limits, dictated by the geometric capacity of the underlying K4 simplex. Physical reality holds together because the precise geometry of the Einstein coupling provides the essential clamping force, preventing our informational universe from dissolving back into pure computational noise.